गुड। डॉक्टर रवि चांद भी आए हुए ने। डॉक्टर साहब की हाल है?
नहीं, डॉक्टर साहब ने अपना वीडियो ऑफ की है, जो तैयार होने है।
अच्छा, तैयार
हाँ
होने।
ठीक
है, गुड।
अजय सिर्फ अपनी
चोपड़ा इज आल्सो हियर। शी इज इन
वो अपनी सीट सिर्फ रिजर्व करके गए हैं, भी सीट रिजर्व कर ली है।
इंडिया हैज आल्सो जॉइंड। वेलकम।
हेलो विभा। विभा माइक ऑफ कीते।
हेलो सर, गुड मॉर्निंग।
गुड मॉर्निंग डॉक्टर विभा, डॉक्टर बिंदिया, गुड मॉर्निंग।
गुड मॉर्निंग डॉक्टर बिंदिया।
हेलो बब्बर। हेलो।
हाँ जी, वेलकम डॉक्टर साहब, वेलकम।
हाँ जी
डॉक्टर साहब, बहुत इंतजार कराया तुसीं अपना ऑफ कीता है सी वीडियो।
हाँ जी, अभी पता नहीं की कुछ ऑफ है वीडियो।
कोई गल नहीं, ਅਸੀਂ ਆ ਗਏ ਹਾਂ, ਹੁਣ ਔਨ ਕਰ ਦਿਆਂਗੇ ਸਾਰਾ ਕੁਝ।
डॉक्टर साहब गुड मॉर्निंग। ਤੁਹਾਡੀ ਤੇ ਗੁੱਡ ਮਾਰਨਿੰਗ ਹੈ। ਕੀ ਹਾਲ ਚਾਲ ਹੈ?
हाँ जी,
गुड इवनिंग।
बड़े बड़े लपेटे हुए जे
डॉक्टर अतुल जी। डॉक्टर अतुल जी, डॉक्टर बब्बर जी ਲਈ गुड इवनिंग भी बोल दिए। ਉਹ ਹੈ गुड इवनिंग डॉक्टर साहब।
ਇੱਥੇ ਤੇ ਗੁੱਡ ਲੇਟ ਈਵਨਿੰਗ ਹੋ ਗਈ ਭਾਈ।
ਚਲੋ ਗੁੱਡ ਲੇਟ ਇਵਨਿੰਗ ਡਾਕਟਰ ਸਾਹਿਬ।
ਇਟਸ 10:30 ਯਾ।
And still you are dressed.
ਤੇ ਕੀ ਕਰੀਏ ਹੁਣ? ਯਾ ਤੁਸੀਂ ਜ਼ਬਰਦਸਤੀ ਕਰਵਾ ਦਿੱਤਾ।
ऐसे काम जबरदस्ती ਹੁੰਦਾ है।
ਹਾਂ। ਇੱਕ ਤੁਸੀਂ ਤੇ ਇੱਕ ਡਾਕਟਰ ਬਿੰਦੀਆ ਦੋਨੋਂ ਕਾਫੀ ਦੇਰ ਤੋਂ ਕਹਿ ਰਹੇ ਸੀ ਤੇ ਸ਼ਰਮ ਆਂਦੀ ਸੀ। ਹੁਣ ਤੇ ਯਾਰ ਇੰਨੀ ਵਾਰੀ ਕਿਹਾ, ਹੁਣ ਤੇ ਕਰ ਹੀ ਦੇਣਾ ਚਾਹੀਦਾ। ਹਾਂ। ਸੋ ਹੋਰ ਡਾਕਟਰ ਰਵੀ ਚਾਂਦ ਜੀ, ਤਬੀਅਤ ਠੀਕ?
ठंड भी रंग दिखा रही है, काफी सर्दी हो गई।
ਓ ਯਾਰ ਓਕੇ। तो आया ਤੁਹਾਡੇ ਤੇ ਜੋ ਅੰਦਰ ਹੈ ਉਹੀ ਬਾਹਰ ਹੈ। ਸਾਡੇ ਹੁਣ ਬਾਹਰ ਤੇ ਬਰਫ਼ ਪੈ ਰਹੀ ਹੈ ਤੇ ਅੰਦਰ ਅਸੀਂ ਠੀਕ ਹੀ ਹਾਂ। ਯਾ
कौन?
ਅੱਜ ਸਵੇਰ ਦਾ ਸਨੋ ਸਟਾਰਮ ਆ ਰਿਹਾ ਅੱਜ ਤੇ। ਸੋ ਡਾਕਟਰ ਸਾਹਿਬ, ਤੁਹਾਡਾ ਦੂਸਰਾ ਅਕਾਊਂਟ ਕੀ ਹੈ? ਉਹ ਅਮਿਤਾ ਚਲਾ ਰਹੇ ਨੇ?
Amita is our staff member.
Yeah, so she's using the other account. Dean Alumni GNDU is also there.
That is Miss Amita Sharma is there. She is the host for today's meeting.
Okay.
She has organized the link.
Okay.
So Ravi Kumar Jan from Taiwan has joined to listen to you. He was my former PhD student and now a postdoc at Taiwan. Welcome, Ravish.
Thank you, sir. Thank you. Greetings to everyone, sir.
Thank you. How are you, Ravish?
I'm very, very fine, sir. And recently joined here, so getting adapt to the new environment.
Okay.
काम शुरू हो गया उधर रविश?
सर हाँ जी, लैब थोड़ा काम शुरू हो गया, बट हले थोड़ा वीजा ਦੀਆਂ ਫਾਰਮੈਲਿਟੀਜ਼ ਇੱਥੇ ਕਨਵਰਟ ਕਰਵਾਉਣਾ ਪੈਂਦਾ, ਤਾਂ ਪਹਿਲਾਂ ਉਹ ਕਰ ਰਿਹਾ ਸੀਗਾ ਤੇ ਅਦਰਵਾਈਜ਼ ਥੋੜਾ ਸਿਮੂਲੇਸ਼ਨ। हाँ जी,
मतलब वीजा भी कन्वर्ट कराना है इन्होंने? ये क्या?
हाँ जी सर, ਪਹਿਲਾਂ ਸਿੰਗਲ ਐਂਟਰੀ ਵੀਜ਼ਾ ਮਿਲਦਾ, ਫਿਰ ਇੱਥੇ ਰੈਜ਼ੀਡੈਂਟ ਵੀਜ਼ਾ ਮਿਲਦਾ, ਦੈਨ ਯੂ ਹੈਵ ਟੂ ਕਨਵਰਟ ਇਟ ਇਨਟੂ ਏਲੀਅਨ ਰੈਜ਼ੀਡੈਂਟ ਸਰਟੀਫਿਕੇਟ। ਤਾਂ 3 ਸਟੈਪਸ ਪ੍ਰੋਸੈਸ ਹੈ ਇੱਥੇ।
तो Babbar साहब, we will wait for another 2 minutes, then we will start.
Yeah, that's true. ਬਾਕੀ ਜਿਹੜਾ ਨਵੇਂ ਜੁਆਇਨ ਕਰਾਂਗੇ ਨਾ, ਉਹ ਅਸੀਂ ਇੰਟਰੋਡਕਸ਼ਨਸ ਐਂਡ ਤੇ ਰੱਖ ਲਵਾਂਗੇ।
हाँ जी, बिल्कुल। Hirdesh has also joined, my former PhD student, now working in a college.
अच्छा, ठीक है। हेलो hirdesh। ये कितने ने आजकल hirdesh
आजकल एक कॉलेज में है जी, दीनानगर में।
अच्छा, ठीक है।
He has got 2 postdocs. Maybe next year he may join one of them.
Okay, that's good. Yeah. And Dr. Vibha Chopra bare dasso thoda. I don't know them. Her.
Vibha is a former PhD student of Professor Lakhwant Singh. Now she is faculty in DAV College in Amritsar.
Okay. DAV College केड़े वाला?
हाँ जी, हाथी गेट वाला।
ਹਾਥੀ ਗੇਟ ਵਾਲਾ ਉਹ ਤੇ ਯਾ ਅਸੀਂ ਉੱਥੇ ਹੀ ਪੜ੍ਹੇ ਹੋਏ ਹਾਂ
ਬਿਲਕੁਲ
yeah
So, sir, good evening to you, sir. So, myself, Dr. Vibha.
yeah
Then you are alumni of DAV College, Amritsar also, right?
yes of course yeah so I did my pre-engineering and then BSc second year and third year from there.
Anand Paul
Okay.
has also joined. Welcome, Anand.
ਹਾਂਜੀ ਡਾਕਟਰ ਸਾਹਿਬ ਡਾਕਟਰ ਆਨੰਦ ਜਿਹੜੇ ਨੇ ਉਹ ਵੈਕੇਸ਼ਨ ਤੇ ਨੇ ਸੋ ਹੀ ਇਜ਼
Acha, he will remain silent then.
ਕੈਲਗਰੀ ਤੋਂ ਜੁਆਇਨ ਕਰ ਰਹੇ
Hungary to ne?
ਨਹੀਂ ਕੈਲਗਰੀ ਵੈਸਟਰਨ
Acha,
ਕੈਨੇਡਾ
acha.
yeah
Dr. Neena Bedi from pharmacy, I think she joined. Yeah, she's also here.
okay
Yeah, good morning, sir.
hello Dr. Neena, how are you?
I'm good, sir. So, welcome to our meet.
Oh, thank you yeah
So we are going to have house full in the next maybe 5-7 minutes.
okay good so how do you suggest everyone to mute themselves when the talk is going on?
The others will mute. After I give your introduction, we will all mute and then you can proceed.
Okay, good. Dr. Arun is also joining. Hello, Dr.
Good morning, sir.
Good morning.
How are you, sir? Because here is good morning.
Thank you.
Morning, all.
Yeah, I think I'm the only person, maybe Dr. Anand also, who have good evening. Otherwise, all
are
of you
good
have
morning. Hanji.
Yeah.
Okay, sir. Thank you, sir.
Yeah. ये एक्चुअली टाइम जो है ये इसीलिए सिलेक्ट किया था ताकि आपको सूट करे इन इंडिया.
Yes, sir. That's good, sir.
Yeah. And it's Sunday, even 9 o'clock Sunday morning is early for you, I know. So
it's perfect, sir. Perfect, sir.
Okay, great.
I think so, Dr. Babbar, it is best for me this time. I'm in BC at 7:30.
Yeah, I know. BC Calgary you are in BC. Yeah, I forgot. Okay.
I'm in BC, so for me it is the best time. 7:30 in the evening.
Yeah. How are
Welcome,
you
Dr.
there?
Anand Pal Singh.
Yeah, hi Atul.
Hi ji. Hello.
Yeah, so Dr. Anand Pal Singh ਜਿਹੜੇ ਨੇ he's our colleague as well as a member of executive of Eastern Canada chapter. So he's on vacation right now. So thank you, Dr. Sir, for joining.
So, shall we start, Dr. Babbar?
Yeah.
So let me begin with your brief introduction.
Okay.
My namaskar, sasrikar, good morning, good evening to all the dear colleagues. So today we have with us Dr. Vijay Kumar Babbar. He is of course an alumnus of Guru Nanak Dev University, and he is also our Vice President of Alumni Association Guru Nanak Dev University from abroad, and he's also the President of GNU Eastern Canada chapter. Dr. Vijay Kumar Babbar is presently a senior research scientist at the Canadian Nuclear Laboratories at Chalk River in the Ontario state of Canada. Chalk River is famous for Professor Brockhaus, where they did some pioneering neutron scattering experiments. And Dr. Vijay Kumar Babbar is at the same organization. Dr. Babbar obtained his MSc in physics in 1983 from Department of Physics, Guru Nanak Dev University, Amritsar, and PhD in physics under the supervision of Professor R.K. Puri at Indian Institute of Technology in 1989. And thereafter, he worked as a scientist in DRDO laboratories at Jodhpur. He was a faculty member at Thapar University and also a faculty member at Department of Applied Physics Guru Nanak Dev University. He immigrated to Canada in the year 2001 and joined Queen's Universities and the Royal Military College at Canada, Kingston, Canada, where he worked on a number of industry-related projects, mostly on electromagnetic, non-destructive evaluation techniques. And he worked on some defense-related projects where they use NDT to examine submarine hull and defense aircrafts. He has worked as an adjunct faculty at the Queen's University and Royal Military College. Since 2014, he is working as a senior research engineer at the Canadian Nuclear Laboratories at Chalk River. And his current research work involves non-destructive techniques and tools for inspection and maintenance of steam generators in nuclear power reactors. He is a licensed engineer in Ontario, Canada, and his expertise is in magnetic materials. I remember right from his days in applied physics department at GNDU, he was working in magnetic materials, on ferrite materials in particular, and he has done some very outstanding work in magnetic materials, neutron diffraction, magnetic flux leakage, eddy currents and pulsed eddy current techniques. All these techniques are used for detecting leakage or cracks in gas pipelines and oil pipelines and military aircrafts and Navy submarines. He has authored 2 undergraduate books, very popular books on nuclear physics and solid-state physics. And these 2 books are published by S. Chand Company in India, and they are very popular books with a very large circulation. He has authored over 100 research papers and technical reports. So my great pleasure to have my former colleague, Dr. Vijay Kumar Babbar with us. And I request him to kindly share his experiences and journey from Guru Nanak Dev University to Canada, and also tell us about his professional work that is doing presently in Canada. Thank you, Dr. Babbar, and over to you. So I request others to kindly mute themselves.
All right. Thank you very much, Dr. Khanna. That was a very warm introduction. I was just wondering if you will leave anything for me to tell in addition to what you have told. Yeah, so you have rightly told everything. You have briefly touched all my institutes and my main work on magnetic materials and other things. You know me very well, so obviously you have no problem telling about me in detail. So thank you very much. I also want to thank especially Dr. Bindia, who has been pursuing me for a long time to give a talk. So thank you very much. And I know she's a very dynamic I would say leader, because she's leading Alumni in a number of ways. So also I want to thank my colleagues, Dr. Ravi Chan, Dr. Nand Singh, and all other, Dr. Vijay Kumar, some my colleagues, my friends, students, for joining today. I know I already told this is Sunday morning for you. So it's not a good time for you. So not a good time for me also, but you know, I'm feeling privileged to be here today and speak with you. So I have no issues, but thank you very much for joining on Sunday morning. So I'll start with my presentation, and I think I need to click this link. Let me know if you won't be able to see. Okay. Chrome cost. So can you...
Now we are seeing something.
All right. So can you see the first slide?
Not visible.
Okay.
Actually,
it can be done in presentation mode only.
See.
Yes, we
What's
can
that?
see.
We can see.
Yes.
Is it good? Okay.
Yes, sir.
Yes.
Yes, sir, we can see.
All right. So I have briefly introduced everything, all my work in this presentation. So I thought, it is the first talk I'm having with you. So many of you don't know me, so it would be better if I touch different things right from the beginning, like from the day I was in GNDU and then further on. So whatever Dr. Khanna told, you will find in these slides. So in the agenda, it's very simple. I'll first start with my early professional experiences in India, followed by my research experience in Canada. So this will cover up almost all the slides, and then finally I'll summarize. And I was thinking it would be better to keep introductions at the end, and any discussion we need obviously will follow at the end. So yeah, so this picture is my favorite picture. This reminds me of my days at GNDU in 1983 when I was in the physics department. So ours was the first batch, probably you know all. So I think you can recognize many of the faces here. So this circled one is me. Unfortunately, we have also lost a couple of friends from this picture. But this picture always, brings me back all the memories. I can even recognize where this picture was taken. So I don't think much has changed ever since. So this was in 1983 when I completed my master's in physics. So I then went on to do my PhD in IIT Delhi, as Dr. Khanna mentioned, and my work was on magnetic ceramics, which is basically ferrites. So I worked on manganese-zinc nickel and manganese-zinc cobalt ferrites. These are substituted ferrites, and we prepared these materials by conventional ceramic technique as well as hot pressing. And the aim at that time was the recording had applications, although this technology is now old now. It's no one uses these recording heads these days, but at that time it was a very new technology. So I'm talking about like 1984 to 1989. So after PhD, I was lucky to have a job right after PhD at DRDO, DLJ, Defense Laboratory, Jodhpur, where I worked on hexagonal ferrites. So being a defense lab, their interest was in microwave absorbers, radar absorbing materials. So these materials, they are supposed to be absorbing microwaves so they are applied on defense structures. It may be aircrafts or other structures, tank or something. And then the radar signals are supposed to be absorbed. So this is the application of these materials. The frequency band in which radars operate is X band, that's 8 to 12 gigahertz. So we were working on basically barium and strontium hexagonal ferrites, which have these kind of properties. So if you look at their absorption coefficient, that is quite high compared to reflection coefficient. And so absorption and transmission coefficients are the parameters that matter in this case. So then I went on to, somehow I felt that I have taste in teaching, so, and I also wanted to go to Punjab, closer to my hometown. So I picked a job in Thapar Institute as faculty in material science. So there, in addition to teaching, I was involved in research on low loss ferrites, and also I continued working on microwave absorbers. Although it was a new kind of setup, so we were building new labs for material science. Material science was the new department at that time at Thapars. So we were the kind of pioneers, and so we were working hard along with Dr. Anand was also there, so he must be remembering. So we all were working hard to set up the labs. So we didn't have any good research group there, but nevertheless something kept going. After 2 years, I was there for 2 years. So after 2 years, I joined GNDU in applied physics, and that's where Dr. Khanna met me, and we were colleagues for several years. So again, I continued that work there in low loss ferrites and microwave absorbers. So there we built a good lab, and we bought quite a bit of equipment, and we got 2 PhD students. So they obtained PhD under me, and also like Dr. Sukreen Bindra is not here, but she was also quite involved in radar absorbing materials and hexagonal ferrites. So I think she is still working on ferrites. So it's the same work that I started, and she is still continuing. I'm so happy that she is continuing. So in 2001, I moved to Canada. The reason I came here was because when I was there, I got postdoc from Queen's University. So I was lucky to land here with job in hand. And so I'll tell a brief. I'll tell my work on different things at Queen's University in next slide. But in addition to Queen's University, I was also working as faculty as well as a research associate at Royal Military College. And then finally, I'm now working at Canadian Nuclear Laboratories. So coming to Queen's University, I told you I got the job in hand, and that was basically in engineering physics department at Queen's University on oil and gas pipeline projects. So what they were doing was they were working on study of flaws in oil and gas pipelines. You might be aware that there's a long length of pipelines, several thousands of kilometers on the surface of Earth as well as under the sea that are transporting oil and gas throughout the world. So although now the trend is that people want green energy, but still there's a several thousand kilometers of pipeline that are working and that are servicing. And with time, the corrosion occurs. So whenever corrosion occurs, there may be flaws, and if a crack develops, there's a leak, and sometimes major accidents happen. And if any of these accidents happen, especially in developed countries, it becomes a big issue. So there's a significant research work going on in this area to kind of find out. So they routinely inspect these pipelines by passing probes and different kind of probes and other what they call pig. So they keep on investigating these pipelines to find flaws and to find out what's the remaining life. And if they find something, they plug that, they replace the section, and this is how they are doing. So it's very difficult to understand these signals. There's a little video I'm not going to show you, but I have a link here. Maybe I can show you. Yeah, I had my YouTube open. So it's a very small video. I think it's 2 minutes. So maybe it will create your interest. So just give me a second. Yeah, I'm not sure if I'll be able to show this. Anyway, so link is there. I'll leave it to you to watch later on. I don't want to do something that closes this presentation. So, all right. So let's go back to the presentation. Okay. So what happens is they use principally the technique called magnetic flux leakage. And the principle here is very simple, that they saturate, they magnetize the steel pipe. In this picture on the left-hand side, you see a horizontal plate, gray colored at the bottom, which is called pipe wall. So they use permanent magnets to saturate this plate with magnetic field, and if there's a flaw, and because of change in reluctance, some of the flux lines leak out, and those flux lines are captured by some kind of sensors. It may be gallium arsenide sensor, or it may be a coil, another coil. So most of the time in the lab we used to use Hall sensors. So these sensors, they pick up the signal. Okay, depending on what kind of flaw it is, whether it's on the near side or on the far side, these signals may vary. So these signals are captured and then analyzed. Now these signals obviously don't say that, okay, we are from this kind of flaw. This is where the research comes. We don't know what kind of flaws will produce what kind of signals. There's corrosion. There are all kinds of messy thing there. So it's a big research work to understand these signals. So we use not only experimental setup in the lab, but also modeling very frequently to understand these signals. On the right-hand side, you see a model where a dent has been created, and this is a magnet, red-colored magnet. So this magnetizes this, and this is how we model and produce simulated signals. So these models help us understand that what kind of flaw is going to give what kind of signal. So this is another example of the same technique. This project was sponsored by Department of National Defense Canada. So on the left-hand side, you see the submarine. This is HMCS Chicoutimi submarine. Canada bought many of these submarines from United Kingdom, from England. So what happened, after some time, they detected flaws in the form of cladding. So cladding is basically, so this is quite a thick steel, it's probably, the wall is an inch or more than that. So if a part of it is missing or corroded, and you you cover that with some type of filler material. That's what we call cladding. So you cover it with filler material and then paint it so it gets hidden. So these kind of flaws, and also they suspected that there might be cracks also. So those flaws they were interested to find out. So these submarines, they are removed from water. I don't know how frequently, but once in a while they are removed from water, but and analyzed. They are scanned, all the bodies scanned throughout, and the signals are analyzed to find out any flaws. So I was a part of the team. I was lucky to be a part of the team to do this work. And on the right hand side, you see my pictures. I'm sitting right on top of this submarine. So and it's quite big. You don't realize this. I wish there was a man sitting here, but this is probably the height of like 10 men or something. That's so big. So that was a good experience, and I'm not going to show all the details what I found, but it was a successful trip. So this was in BC, where Dr. Anand is right now. It was in Victoria, Victoria City in BC. So this is another project sponsored by Department of Transportation, US, and Gaz de France at Paris, France. So they wanted us to study stresses, because it's basically a related project where I told you that the pipelines develop flaws. Now, you might be aware that these pipelines operate under pressure. So this oil and gas that flows through it, that's not at normal pressure, that's at high pressure. So when the pressure is high, the stresses build up, and those stresses further can cause damage. So what I mean is, like, if a crack has to develop, let's say after 10 years, and if the pipeline is under stress, the same crack can develop after maybe 2 years or 3 years. So these stresses worsen the situation. So the aim was to study the effect of stresses. Now, so we use neutron diffraction for that, and principle is very simple. You all know Bragg's law for X-rays. Same applies for neutrons. So when the stress happens, the unit cell changes, dimensions of the unit cell changes. So interplanar spacing change, and those changes you can determine by neutron diffraction. So that's another NDE technique that we use, and it was started at Royal Military College, but we are still continuing at CNL, Canadian Nuclear Laboratories. Now, you don't have to go through all the details here, but I just wanted to show this picture to give you principle for some of you who are not aware of the basic physics. So what happens is, if you look at the picture on the left-hand side, the red one is a coil through which a current is passed. So this current produces magnetic field, which is the blue lines. So that magnetic field that interacts with a conducting material placed nearby and produces eddy currents in the material. And those eddy currents in turn produce their own magnetic field, which then is captured by the either same coil, or you can have another coil which we call pickup coil. So so this is the principle. So this induced magnetic field basically changes the inductance of the coil, and that's what gives a different voltage in the form of a signal. Now, there are two related techniques. One is called eddy current, second is called pulsed eddy current or transient eddy current. They are similar, except that the application is a little different. In pulsed eddy current, we used pulsed excitation, like square wave instead of sinusoidal excitation. So the advantage of pulsed eddy current is it has larger skin depth. Eddy currents have skin depth given by this formula, the first formula in the middle, and the pulsed eddy current is the extreme right. So theoretically, the skin depth of pulsed eddy current is almost 1.8 times that of the normal eddy current. So this pulsed eddy current is what gives you an edge over eddy current, especially in some applications. So this is one application where I'm showing you two aircrafts. So these are CC-130 Hercules and CP-140 Aurora. These both are Canadian defense aircrafts still in use. So what they were seeing was the cracks in the lower layers. So on the left hand side, under CC-130 Hercules, if you see the lower picture, so what you have here is the wing. Horizontal plate represents wing, and the lower part represents the spar. Spar is basically a support that is used to support the wing structure, and these two are connected by fasteners. So what was happening? The crack was appearing in the lower layer, just near the end of the fastener or in between the two layers. So same was happening on the right hand side. The only difference is in the right hand side, the two layers are attached by a lap joint. So this is a lap joint. If you know mechanical a little bit, so lap joint is when two layers of metal overlap each other and then fastened by something, maybe fastener or something else. So this kind of, now the access is only from the top side. Access is not from the bottom side. The bottom side is inside the wing structure. Now how to find flaws when you have access from the top side? So there's no conventional technique, like eddy current cannot do it, ultrasonic cannot do it, because it's the second layer. So pulsed eddy current is the only alternative in this case. So typical crack length may be like 1/10 of an inch, and this plate is 1/4 of an inch. So it's quite a thick plate. It's not thin. So pulsed eddy current was used for this purpose, and it was quite successful. I haven't shown the signals or details because I thought that will become boring. But this is one application of pulsed eddy current where we got quite a bit of success. Now, coming to Canadian Nuclear Laboratories, where I work now, the CNL has very interesting history. Dr. Khanna told you a little bit about Brockhaus. So it all started, I think, after Second World War. So when so many things happened and the nuclear technology was used in Japan, so Canada also thought, oh, we should have our own nuclear technology. So they started. I don't know, like now they don't say, but what I believe is they must have started with the name of making a bomb, but Canada never made it and always used this for peaceful purposes. But this place was very secretive, a small town, Chalk River. Still, it's a small because government never allowed it to develop industrially. So it still has a population of maybe Chalk River, maybe 1,300. And then there are satellite towns in the neighborhood that have large populations. So most of the employees work at Chalk River and then go to the neighboring villages or towns to live. So this is a very interesting history. But the point is, this place has all the PhDs, all the engineers, masters. Okay, so at one time, even now, maybe the Deep River, which is just 7 kilometers away, was ranked as the most educated town in Canada. So it now has a population of 3,500, I think. So, so what they did at Chalk River, they built a reactor called NRU, National Research Reactor. So this is a research reactor, small reactor, not high powered. But this technology was used, this became a foundation of CANDU technology, CANDU power reactor technology. CANDU is the acronym for Canada, Deuterium, Uranium. And they, I think this NRU was commissioned in 1957 or something. These are very interesting YouTube videos in case you want to watch later on. So these are the links. So they, so now it's closed basically. Now it's decommissioned because it was almost 50 years old, and a couple of times there was leakage. So they shut down this reactor. So this has become a history now. But this was producing cobalt-60 isotopes and supplying worldwide for cancer treatment. So this CANDU reactor technology that was developed at NRU, at Chalk River, that was supplied in the form of CANDU reactors worldwide. So India also has one CANDU reactor in Rajasthan. I think 2 units are CANDU, and I think it's called RAPS, Rajasthan Atomic Power Station. So 2 units are CANDU, and then other units, India built its own. That's called, I think, Indian heavy water reactor, something like that. So this is the air view of the Chalk River I was talking about, and I told you a little bit about this. So it's about 9,000 acres in size, 200 acres lab complex, 70 nuclear facilities, 70 major buildings. Still, it has more than 3,000 employees, and many of them are engineers and scientific staff. So for those of you who are interested, this is how the CANDU pressurized heavy water reactor is. This CANDU technology is basically different from other reactor technology because in the way that it uses excuse me. So it uses heavy water instead of normal water. So it uses pressurized heavy water, and also it uses normal neutrons. Like instead of thermal neutrons, it uses fast neutrons. So those are the 2 differences in CANDU compared to other reactors. So in this picture, what you're seeing is starting from the lower side, this is where the core of the reactor is. So the green one is a heavy water moderator. The yellow lines, horizontal lines, are basically fuel channels where the fuel is. Those little dashed lines are uranium pellets. So the heavy water coolant flows through them to to moderate the neutrons. And then this whole yellow circle of pipes is basically called the primary side. And then if you come to the top, the blue ones are steam generators, where there's normal water flowing through, entering from the lower end and leaving at the top end. So at the top you get the steam basically. So the hot water from the yellow pipes transfers thermal energy to cold water, which is in the blue region, and then cold water heats up, boils, produces steam, and that steam is used to run turbines and then to produce electricity. So that's the basic principle. This is the same thing. Yeah, that's what I was telling you, that this is RAPS in Rajasthan, India. So it's a little more complete picture, but basically the same thing that I showed you before. So I'm not going to go much into details here. So this is just a picture of the core, the core shell, which is a huge cylinder with the number of pipes. Number of pipes going through this. The pipes are not shown for clarity, but those little marks are the pipes. On the right hand side, you see the same thing in the vertical view, the top of the reactor, at the very top horizontal plate. And yeah, so there's nothing much information other than just to show you that this is how the reactor vessel looks like. This is the internal picture of NRU. So in the middle you see a huge circle. That's what I was showing you in the previous picture. So that's the core of the reactor. So by the way, this NRU, at NRU, we were not producing any electricity. This was purely a research reactor. We were using neutrons for experiments, neutron scattering or diffraction. And there were so many other experiments going on. Isotopes were being produced using neutrons, but we were not producing any electricity from this reactor. Yeah, for those who are from non-physics or non-nuclear background, I just thought to throw in this slide that how much energy you can produce from uranium. So 1 gram of uranium-235 gives you about 82 billion joules of energy. So this is how you can compare that the 3 barrels of oil, which is 42 gallons each, or 1 ton of coal. This is what 1 uranium pellet can give you. So there are similar equivalents at the bottom. Now coming to the work that NDE work that I do at Chalk River. So basically all our work is related to steam generator. So on the right hand side you see the steam generator. It's not a part of the core, so core is separate. So from the core, I showed you in the previous picture that the water comes and water enters through the tubes at the bottom. I don't see it's clearly shown here, but the water enters at the bottom and then leaves at the top. So there are a number of vertical tubes, thousands of tubes in the steam generator through which the water flows. So inside the tubes, it's heavy water. Outside it's normal water. So the biggest precaution here is that those two waters should never mix, because heavy water is radioactive. So if there's a leakage or any flaw that causes the heavy water to leak into the normal water regime, that's going to be disaster. So reactor has to be shut down to fix that problem. And shutting down a reactor would means each day it's a few millions of dollars of loss. So they do not want that, but they do shut down reactor in a planned manner. I think it's shut down for a few days every 2 years, and all the tubes are inspected, not only tube but other parts as well, like even fuel channels are inspected by various techniques to find out if there are any flaws. So they keep a full record of that, and they observe how the flaws are aggravating as the time passes. So all these texts written here are basically the type of flaws or defects that can happen. I'm not going to read all of these, but this should give you some idea that in steam generator, the tubes can suffer a number of flaws. There are not only tubes, but to hold the tubes together, there are support structures, steel support structures, and these tubes are under the water in these tubes is under pressure, and there are vibrations. So because of vibrations, there may be fretting. So you can imagine all kind of flaws can occur. And so what we basically do is we develop probes, first of all, to inspect flaws, inspect these tubes. So on the left-hand side, if you see the text, so what we do is we develop adequate probes for NDE of conductive materials, in this case, mainly these tubes, and inspect tubular components and structures, and modeling of probe designs and development of prototype probes. Inspection technique development and qualification and support to utilities. Utilities means those like electric utilities, those operate the reactor, those own the reactors. For example, here in Ontario, we have Ontario Power Generation. They have their own reactor. By the way, for your interest, in Canada, we have 6 reactors. So all the reactors are basically come to us for these inspection techniques. Now, to develop probes, there are different types of probes, and to develop them, because you have to sense, you have to inspect different kind of regions, different geometries, different kind of flaws. So one probe is not enough for everything. So we have a number of probes, and also to develop these probes, we mostly use finite element modeling. So this is an example of one model where, you know, so these holes represent the regions where the tubes enter or leave the plate of the reactor. So idea is just to show you that how these probes development work goes on. This example of some of the probes. On the top left, you have a few pictures. The most common probes are bobbin probes and X probes. So bobbin means just a bobbin type of coil. And on the right-hand side, top right, there are X probes where you have basically 3 rows of very tiny coils. So the idea is to detect axial as well as circumferential flaws in one scan. And then there are other kind of probes. For example, on the left-hand side, at the lower side, it's a rotating probe. So you see the coils, and these probes are rotated when they enter into the tubes. So again, the idea is to scan the whole circumference of the tube. So this is just one
Thank you, Professor Babbar. Very nice presentation, very interesting work. I may mention here that the Cyrus reactor at Bhabha Atomic Research Center in Mumbai, that is also a CANDO type reactor.
Oh, okay.
And now it is closed after we signed a nuclear agreement with United States.
Okay.
And that's also a pressurized heavy water reactor. In fact, all the Indian nuclear power stations, they are PHWR type reactors.
Yeah, okay.
And some of our pioneers in neutron scattering at BARC, Dr. B.A. Dasanacharya, P.K. Iyengar, K.R. Rao, they got their training in neutron scattering under Brockhaus in the early 1950s.
Okay.
So CNL is very important for our pioneers in neutron scattering.
All right, that's good. Yeah, I remember you did some work at BARC. Did you? I remember you used to go to BARC for some work or something.
Yes, we use their neutron diffraction beamline.
Neutron diffraction
reactor.
Yeah. Okay. Yeah.
And I also started my career from BARC.
Yeah, that's what I remember. Yeah.
We still use their neutron diffraction beamline.
Okay.
So how many reactors you are having at CNL right now?
No, at CNL, NRU was the main reactor. Now there's another one called NRX. Okay, that's also a small research reactor. So what CNL is trying to do now is they are trying to bring small modular reactors. Okay, so I haven't touched that topic because I'm personally not involved in that, but this is the technology that CNL is trying to bring. Are you there, Dr. Khanna? I think you...
Yes, I'm here.
Okay, yeah. So what small modular reactor is, it's basically a smaller version of the bigger reactor. So they build at another site, wherever the company exists, and then they load on trucks and bring all the modules and assemble on site. So they are like small reactors, less than 300 megawatts, something like that. But the advantage is they are cheap. They're supposed to be safer, and also they are very much suitable for remote communities. Okay, for example, in Canada has a large area of remote communities. where you cannot afford to send basically the wires and all that transformers. If you have a small reactor, just install there, and whole town will get electricity. Demand is not much, so that can be met by small modular reactors. So that's the way we are going. So we are hoping that in the next couple of years, CNL will have the first small modular reactor.
So, hi, Babbar.
Yeah.
So it was a nice talk.
Thank you, Dr.
Yeah, my question is that what is the future of nuclear energy in Canada?
Mm-hmm.
And have you any sort of alliance with the Triumph, which is at BC?
Yes, we do. So what I presented here is only what I'm involved with, but CNL has diversified after this NRU was shut down. The CNL has diversified in a number of areas. Triumph collaboration is one. I think they are also trying to make some isotopes by collaborating with Triumph, and they are also doing a lot of work in hydrogen technology. Okay, so they have got projects from transportation department in Ontario to run this Toronto subway system on hydrogen technology. So they have diversified in a number of other things. Recently, there was a kind of agreement signed with Germany to some form of collaboration. I don't know the details, but what I'm trying to say is they have diversified. So they are in pretty good shape right now. Like for the last, even after a pandemic, for the last 2 years, the company has done pretty well.
And what is the future of nuclear energy in Canada?
Nuclear energy, it's considered to be green energy. So people, this course recently happened. So they are trying to set a target to eliminate oil and gas. Okay. So now, what's the option? This electricity, if you think wind will provide or solar will provide, it's not going to happen. Wind and solar cannot meet the demand. The only way is nuclear. Okay.
Right.
So nuclear is still safer, although accidents may happen, like accident happened in Japan and other places, but it's still considered to be safer compared to safer and cheaper. Okay.
Yeah.
So if we have to meet the deadlines to produce green energy, we cannot skip nuclear. Nuclear is going to be the primary. Okay.
Right.
Yeah.
Thank you.
Sir, I have a question.
I think your voice.
Sir.
Yeah.
Sir, I have a question.
Go ahead.
Actually, I want to ask, what are the opportunities for postdoc in Canada? So what kind of fellowship one can to work for postdoc also?
Now situation is much better in the sense, first of all, after this CNL became corporation, they have kind of relaxed rules. When I joined, there was so much strict security, like you have to have Canadian citizenship, then you should be living here for 5 years. But now, even if somebody is here for 1 year, or sometimes even a new, but they find appropriate person with good qualification, they can hire it. So in general, I would say the chances are there. The only thing is you have to fit into the right group. You should meet the requirements they have. Okay, so yeah, so that's what I say, that I think the things are not bad. Okay, but it all depends on which group you apply and what kind of demand they have. I would encourage you to continue looking at the website www.cnl.ca. So, but they certainly hire students, they hire postdocs. Yeah, so and we need all kind of people. So
I mean, one has to be in Canada before applying for the postdoc, or we can apply from India directly and come for the postdoc, right? Like usually, I'm working in radiation dosimetry field, and I got my patents also in that field. Recently, I had an international patent.
So to be honest, ever since this corporation came, okay, they are all American people, and they are in Canada to do a business and to run the lab nicely. Okay, so they don't care where you come from. If they find the right person, they can call from anywhere. It doesn't matter. Okay, so you have to show through your resume or your phone interview that you are the right person. So I wouldn't stop you from applying, although I do agree that if somebody is here, then the chances are better. Okay, but that doesn't mean that you are ineligible. Okay.
Karamjit Singh wants to ask something. Yes.
Yeah. Sir, very good morning.
Hi, Karamjit.
Sir, good morning.
बोलो, आवाज नहीं आ रही.
सर ਲੈਕਚਰ ਬਹੁਤ ਅੱਛਾ ਸੀਗਾ.
Thank you.
ਸਰ ਜਿਵੇਂ ਆਪਾਂ ਐਨਡੀਟੀ ਐਪਲੀਕੇਸ਼ਨ ਵਾਸਤੇ ਈਐਮ ਤੇ ਐਡੀ ਯੂਜ਼ ਕਰਦੇ ਹਾਂ ਸਰ. ਸਰ ਆਪਾਂ ਕਾਸਟ ਕਮਿਸ਼ਨ ਯੂਜ਼ ਕਰਦੇ ਹਾਂ ਜੀ, ਕਾਸਟ ਕਮਿਸ਼ਨ ਸੌਰਟ ਆਫ ਸੈਂਸਰਸ for crack propagations in the materials or the porous media sort of.
Cost emission, I couldn't understand what that is.
Acoustic emission, sir. Punjabi ਚ ਹੀ ਬੋਲਦੇ ਨਾ.
ਕੀ ਬੋਲਦੇ?
Probably he means ultrasonic.
Oh, ultrasonic. Okay.
Sir, acoustic emission. Acoustic.
Yeah, acoustic. Yeah. Acoustic, ultrasonic. Yeah. Even at RMC when I was there, I think a couple of people are working on acoustic emission. Okay, there are certain applications where acoustic emission and ultrasonic is still, that's kind of their Bible. Okay? Whenever we want to confirm our eddy current signals, we compare with the ultrasonic. Okay, so that's they call it ground truth. But the problem with ultrasonic is it's very slow. Okay, and it doesn't work in certain situations. Okay, eddy current, the biggest advantage is it's fast. Okay, the probes run at like probably 36 or 24 inch per second. Ultrasonic cannot scan that. Okay, so yeah, both acoustic emission and ultrasonic, they are still popular techniques. Especially ultrasonic is very popular. Okay, and
can we detect crack propagation with the help of eddy current?
Sorry, what can you detect?
Sir, crack propagation, sir.
With ultrasonic? Oh yeah. So it depends like where the crack is. I don't know what material you are talking about or what the depth, but it cannot detect in second layer if you have multi layers, like one I was showing with defense aircrafts. Okay, the UT wasn't successful because the cracks were in the second layer. So whenever you have two layers and there's a gap between the two layers, even if they are tight attached with the fastener, but still there's a little bit air, so you'll get a very strong reflection from that region. Okay, so that's why ultrasonic is not going to work there. So if you have a single continuous material, ultrasonic is the best, but best in the sense that in terms of accuracy, I would say, but not in terms of speed.
sir, we have a material having a different density layers, and the density is like 150 kilogram per meter cube. Then we have 117 kilogram per meter cubes. So how to detect the interface?
How to differentiate those?
No, sir. Yeah, how to detect the interface?
Yeah. Yeah, that might be tricky, because if the density is changing continuously, okay, that might be tricky, because to have a strong signal from ultrasonic, there should be a little abrupt transition in impedance. Okay, so if the impedance is changing very gradually, then you're going to have very broad peak. You're not going to have a sharp signal. Okay, so that's going to be a limitation. Dr. Anand Singh, my colleague, I don't know if he's still there. I don't, not now, but he used to work in ultrasonics. So I don't know. Are you listening, Dr. Saab? So he's mute, but I don't know if he's still around. So
I'm here.
Yeah. So have you listened to the question of Karamjeet about ultrasonic? You're a more expert than me.
About the different densities when the ray passes from one higher density to a lower density, or different levels of density.
Yeah.
How that is going to affect his. Yes, it is going to affect. Definitely, the modeling will be totally different. I totally agree what you said, Vijay. Dr. Babbar, what you said, I totally agree to that, because I don't do with metals anymore. I have worked with food materials. I have worked with milk fat, the crystallization behavior in milk fat. And we have seen those problems as the crystallization changes from one region to the other region. The density is going to affect your ultrasonic modeling behaviors. It is going to affect, Karamjeet, definitely.
Okay.
And that calculation you have to input through different modeling aspects. Fourier transform is one of the aspects I have seen, which has really helped me in that part.
So I'm trying to the convolutions, sound convolutions.
Yeah. And Atul also can speak to that. Atul is also from the same ultrasonic group I am from, so he also can speak to that. Yes, definitely you will have those convolution effects, and you have to put those different Fourier transform aspects to it.
Yeah, sound wave propagation depends upon the ratio of elastic moduli to the density.
Exactly.
So if there is a change in that ratio, you will see changes in sound wave velocity propagation. And of course, you need an abrupt change to get a reflection. Abrupt change in density or elastic moduli.
Both the materials are in the same range. I mean, one material has a density of 170 and then another have a 175. So we are not getting any appreciable reflection from that. So that's the problem. That's why I was asking.
Yeah.
And you may have to use some other technique.
Yeah.
Okay. If there is any other point.
Yes. So Karamjeet, actually, whenever we are stuck with these kind of issues, the best way is to model. Okay. So to model and see how it behaves, because model basically gives you an ideal scenario. So if you can see some signal with modeling, then you can expect something in reality. Okay.
Sir, console which try ਕੀਤਾ ਸੀ sir, but reflection on the वैसे नहीं आ रही sir practically.
अच्छा. और फिर yeah, I don't know, maybe थोड़ा फर्क तो ਹੁੰਦਾ ही एक्सपेरिमेंट और मॉडल ਦੇ ਵਿੱਚ, बट आनी चाहिए थोड़ी बहुती.
पता नहीं sir, attenuation भी काफी है, signal ਦੀ ਤੇ scattering भी काफी. So that may be practical aspects are different as compared to the theoretical. Theoretical ਤਾਂ ਆਪਣੇ ਕੋਲ ਸਰ ਚੀਜ਼ਾਂ ਹੁੰਦੀਆਂ ਨੇ, ਉਹਦੇ ਵਿੱਚ ਹੀ ਮਾਡਲ ਰਨ ਕਰਕੇ ਆਪਾਂ ਨੂੰ ਦੇ ਦੇਣਾ.
अच्छा. All right. Any other question? Yeah. Yeah. I've seen Dr. Bedi joining. Namaskar, Dr. Saab.
Radish Bedi is here. Bedi Saab, kindly unmute yourself. So very nice presentation, both informative, very well done.
Yeah,
And
thank you.
we
Thank
really
you.
appreciate it.
Yeah, I would like to quickly have introduction. I think we introduced some of the members already, but those who haven't.
Manu
Dr.
Pandra is here. He is also GND alumnus, presently
Yeah.
with Department of Atomic Energy.
Okay. So I see Sachin Godra. Sachin, can you introduce a little bit in just few seconds?
So, good morning, sir.
Good morning.
Myself, Sachin Kumar Godara. I am basically a textile engineer, but right now we are in chemistry. I also work on ferrites.
Okay.
M-type hexaferrite, barium and strontium ferrites.
Okay. Okay. All right.
So some of the sensors are based on ferrites. That is why I am interested in that. You have also initially worked on ferromagnetic materials.
Okay. Yeah, that's good to know. Thank you. Dr. Arun Upmanyu, yeah, I know him very well, but if others don't know, then he should introduce also.
Okay,
Arun?
thank you very much, sir. Thank you very much, sir. And I'm very lucky that Professor Nanpal is here. Sir, very good morning. Hello.
Good morning, Arun.
Sir, I'm student of Dr. DP Singh. So if you remember, he is also in Canada, and I think you work together in Thapar, sir. If I am right,
Yes,
sir.
we did. Dr. Babbar, myself, and Dr.
Yes, sir.
DP
Yes, sir.
we all work together in Thapar. And Atul, Dr. Atul, Dr. DP Singh, and myself, we are from the same group. We did our PhDs with Dr. S.S. Patti. Yeah.
Yes, sir. I met Patti sir also when he was in Adesh, Director Adesh Faridkot, sir. I met him, sir. And
Presently, Professor Bhatti is in Canada.
Yes, sir. Yes, sir. Now he is in Canada, sir. Actually, I used to talk with Dr. DP Singh, and we are, sir, first of all, very good morning to all of you. I am working as Associate Professor in Chitkara University, Punjab campus, sir. So my area of interest is ultrasonic. I am working with Dr. DP Singh and in ultrasonics proper local interaction, and also, sir, area of interest is X-ray scattering. So X-ray scattering, I'm working with the isotopes, cobalt also, iron, americium also, and at laboratory experiments. So I'm very lucky, and sir, this was very interesting and very nice lecture, because nowadays what I have felt within 22 of my teaching experience, that we are lacking in application part of sciences and technology, especially in India. Because usually people are losing interest in sciences and they are moving towards the engineering part, because we are not able to identify the actual implementation of our subject in technology. As you said, I have taken a screenshot that use of Bragg's equation, a Newton scattering experiment, to identify cracks as well. So that's very interesting, and I wish, and I would like to have one lecture in my university also on same track, sir. Thank you very much, sir, and thank you very much, Nanpal sir, for and I'm very lucky that you all both are here for me. Thank you, sir.
Dr. Professor Bedi has joined us. Bedi Saab, namaskar ji.
फाइन
नमस्कार सर.
नमस्कार. बड़ा अच्छा लेक्चर दिया, और दिस इज अ वेरी गुड platform to interact the students and the faculty of the physics department, and we are really proud that all our many of our own alumni that joined this talk. So this is the best way to interact each other. I really wish the organizers, particularly Dr. Khanna, to organizing such a beautiful lecture. Really, it's very nice.
Thank you, sir. Thank you.
Dr. Bedi, namaskar. Anandpal here. It's very nice to hear your voice after so many years, Dr. Bedi.
Yeah, Radanand, are you in Canada?
Yes, Dr. Bedi, I'm in Canada for the last 20 years now, 20 plus.
Yes, yeah. That's a good. बड़ा अच्छा लगता है हमारे बच्चे जो आगे निकलते हैं ना और उनके इस स्टेज में आगे आवाज सुनते हैं और अच्छा काम कर रहे हैं. Real feel very nice.
Yeah. I want to add a couple of things. First of all, as Dr. Arun said, Dr. Khanna and Dr. Bedi, maybe you should try to introduce more like applied courses or applied component to your courses. We did have a MSc Applied Physics, but like I don't know if it's still there. As I was saying, this nuclear technology is going to grow, okay, because everyone is talking about green technology. So this is going to grow, and these kind of issues like ND issues are going to increase. Okay, so you need to produce the manpower who can handle these things. And I'm sure from 10 years from now, you'll see a number of jobs in this area in India. Okay, so this is going to grow. So this is the right opportunity to start work in these areas. Okay, so that's my suggestion.
Can I add something else also over here? What Dr. Babbar has said. Don't limit your knowledge to only one particular type of materials. You should expand your knowledge of the analysis technique to the other materials also. It's not limit. You will be surprised that what these techniques can be used for. I mean, Dr. Atul spoke about the neuron beam. The neuron beam is right now being used over here also to look at the crystallization behavior in chocolate. It's amazing how these analysis techniques can be used and how much information you can get out of that. And we back home are so limited in just looking at one particular type of material with that particular type of analysis technique that limits ourselves to that area.
Yeah, that's correct. Yeah. Karamjit has some question. Karamjit, you have a question?
Sir, I have a submission. सर क्यों ना अपना एक WhatsApp ग्रुप ही बना लेता जावे?
Already हैगे ने काफी यार. To be honest with you, I cannot handle WhatsApp groups because once I'm a part of a certain group and somebody sends something, I try to look at it. Otherwise, I don't want to be a part of this group because I don't. Honda ki hai ke loki out of the way jaake they start sending all kind of things which I don't like. Okay. So,
sir, I have one request. Since you are alumni of DAV College Amritsar, so I really wish to add you to the group of DAV College Amritsar alumni. So I hope you will not refuse.
So Dr. Vibha, won't it cause the same problem as I was talking now?
No, not at all. It will not cause the same problem because no one send any messages there. Yeah. Only when there is a need, people send and interact with each other.
Yeah. So if you have a coordinator who has
I'm a coordinator. Actually, I'm a coordinator of.
Because if somebody writes something that's not right or that's not good, then you should be able to just remove that person from the group.
Sir, actually, I'm a coordinator of alumni group of physics department, so I'll add you to that group only.
Okay, that's fine. Yeah, so far as because I don't want to be a part of any conversation that's objectionable.
Yeah.
So even if you say, I cannot say, I didn't read it. That's not the excuse because once I'm a part of something, I should.
Yeah.
Okay.
Yeah. So I'll get your number from Atul Khanna, sir.
Yeah, that's
fine.
Yeah.
Yeah. Thank you so much, sir.
Yeah. I see a couple of other people joined Brijmon Gupta is 1 year junior to me, and he's industrialist in Amritsar, and he was, I think, the topper of MSc topper of his class. Brijmon, are you there? Can you unmute, please? Anyway, I think he's not there. Mr. Nirmal Olak, Canada de ne. Nirmal ji, are you from Canada? Just I want to quickly introduce, I think there are a couple more, and then we will close this meeting. Om Prakash ji, Mr. Om Prakash.
Om Prakash is MSc Nanoscience student, and also he did PhD with Dr. Raman Mahajan.
Okay.
Yes, sir. Good morning, sir.
Good morning. How are you?
Yes, fine, sir. Fine. It was nice talk, sir.
Yeah, thank you. Dr. Khanna told a little bit about you. So you want to add anything?
Yes, sir. Actually, I am working now as assistant professor at Khalsa College, Amritsar, sir.
Okay. That's good. You know, I see this is very important that whosoever comes, at least we should have some introduction. So otherwise, there's no point of these kind of sessions. These are supposed to be interactive session. So if we don't have interaction, then it's no use. And Manu Chandra, I think Manu Chandra, I know him. He was there in previous talk. Manu, are you there?
Yes, sir. Yes, sir. And I am amazed and surprised. But before that, Bedi Sahab, Professor Bedi, Professor Atul, मेरी तरफ से आपको गुड मॉर्निंग। नमस्कार। बेदी सर पता नहीं मेरे को रिकॉल कर पा रहे हैं या नहीं कर पा रहे।
नहीं मैं कह रहा, आई एम रिकॉलिंग यू, आई नो यू वेरी वेल। और मनु
तो बब्बर सर टॉक तो खैर अमेजिंग थी।
थैंक यू जी।
टॉक वाज वेरी अमेजिंग, और मैं ये सरप्राइज हूँ कि मेरा और आपका कभी मुलाकात क्यों नहीं हुई। तो मैं ये कोरिलेट करने की कोशिश कर रहा था कि हम थोड़े से ऑलवेज मेंटेन्ड सम डिस्टेंस। जब आपने यूनिवर्सिटी छोड़ी एंटर करी, और जब मैंने यूनिवर्सिटी छोड़ी आपने री एंटर करी।
अच्छा। और हम एक्चुअली क्या था, आई यूज्ड टू लिव इन अमृतसर, सो हम डे स्कॉलर थे, हॉस्टल में नहीं रहते थे। ओके, सो दैट्स व्हाई आई मिस्ड।
मैं भी अमृतसर में रहता था।
चलो नेक्स्ट टाइम आप आएंगे ना, तो आई विल पर्सनली मीट यू व्हेन आई विल कम नेक्स्ट टाइम टू अमृतसर। ओके,
अच्छा मैं थोड़ा सा प्रोफेसर अतुल, इफ यू परमिट मी, थोड़ा सा ऐड करता हूँ इसमें। some of our friends who are talking about the application of these techniques, I just want you to remind you, especially those friends, कि ये जितनी भी टेक्निक्स की बात की है डॉक्टर बब्बर ने, मोस्ट ऑफ देम आर यूनिवर्सल टेक्निक्स, कि जैसे उन्होंने फर्स्ट लेयर सेकंड लेयर की बात की, दी सेम अप्लाइज टू द अर्थ आल्सो। अर्थ की जो पूरी एक्सप्लोरेशन है, दी सेम एडी करंट्स, instead of having first layer and second layer in the aircraft, you have the first layer on the earth crust and then the second layer. Regarding what they were talking about, convolution and all those techniques, I just wanted to inform them that there is a book in our GNU library, Calford and Dobrin. Basically, they are from exploration techniques, but these books deal very well with all the things, questions he was asking. Karamjit, I think he was asking. Thank you.
Thank you, Manuji. Thank you for this information.
Thank you, Manuji. Yeah. So, Dr. Na, I think we have met virtually almost all the participants. So, yeah, so maybe you can give a final remark and then we close it.
So, thank you, Dr. Vijay Kumar Babbar ji. It was great pleasure to listen to your work and achievements. and we are really happy for you. And we wish you all success and happiness in the future. And we hope to meet you soon in Amritsar, India. I hope you can plan a visit next year.
अगर ओमिक्रॉन चला गया थे.
And thanks, Professor Atul. Thanks, Professor Atul, for organizing such a wonderful session and interaction.
Exactly. Yeah, I was going to say that. Thank you, Manu. You stole my words. Thank you very much, Dr. Khanna, and all of you for being a part of this virtual talk. And once again, I say that this was very high level, not any details. I skipped all the details, but if you want me to just focus on one particular area and elaborate more, show the signals, how to analyze and all those things, we can hold that too. But I was hoping that because it's a mixed audience, I should keep it at very high level and very introductory. All right.
Yeah, that was very effective talk. So finally, I thank Ms. Amita Sharma. She is the staff member in our alumni office. So she organized this event. Thank you.
Thank you so much, Amita. Thank you.
Thank you.
So,
okay, then goodbye.
All right. Thank you. Namaskar.
Goodbye to all.
Yeah.
Goodbye.
Bye-bye.
Okay.
Bye.
Bye-bye.
Huh?